Alrighty guys, good morning. Welcome back to Calc 1 Honors. I wanted to let you know I'm here just a few minutes early because I wanted to give you a heads up that I'm going to exert some executive influence today. Um, I did get the materials from our student teacher here today. The original plan was to have Nikita deliver the 3.2 lecture today. Unfortunately, I got those materials this morning and have not had time to review them yet um, because our meeting last week did not pan out. I had not seen Nikita yet. So because I haven't had time to review the student teaching materials and give Nikita an appropriate amount of feedback, just make sure everything is like on the up and up, I think today it would be better to kind of fill in some of the details from Radha and Natasha's student teaching on Wednesday. I know that there were some questions that kind of persisted through that, and also to look at some more examples of problems we can solve using just the materials from 3.1. In the spirit of not wanting to learn math in a circular logic way where you're depending on something you don't yet know, um, and also to make sure you guys are sort of maximally comfortable with the material before we move forwards, I'm going to exert a little bit of executive control here today and say rather than having Nikita do the 3.2 lecture today, I will go back and fill in some of the material from 3.1 that we wanted to talk about on Wednesday, and then Nikita will deliver her lecture on Monday of next week. So she's not here yet. I don't want to charge ahead without having communicated this with her. So let's give her just that 1 minute of time before class actually begins to get here, and then we can get started.
I want to ask, when is the exam, the first exam?
Yeah, that's a great question. Let's take a look at the syllabus. Oh, so here, we can do this together. I'll turn on my screen share. Alright, so once we have finished the section on the chain rule, we will be ready for our first test. Now that would normally be next week, but we did lose a little bit of time due to the holiday. So right now we have covered section 3.1. We're going to spend an extra day on 3.1 today, which is going to set us back a little further. That's okay. We'll do 3.2 and 3.3 early next week. So 3.2 will be next Monday, 3.3 will be next Wednesday, and 3.4 will be the following Friday, or will be that Friday, next Friday. So I'll be able to release your study guide for the exam next Friday, which means that the exam itself will take place. Let's see, are we going to run into any holiday issues here? So,
Could you list the study guide earlier, because I want to do it earlier. I want enough time to.
A little bit. So I'm hesitant to do that. So generally the way I choose the study guide problems based on how you guys respond to the homework problems up to that point. I could release the study guide, but with the caveat that I might add a few problems later. So if you like, I could publish a kind of first draft of the study guide today, but I may add some problems to it next week after we get through this material, because the way I choose those problems is all about how you guys handle the problems in the homework.
That's good.
Okay, I'll do that then. I'll give you the first draft of the study guide this afternoon, and then just remember to check it later, because I will add more problems to it next week. I'm still not seeing Nikita. Is she here yet? Oh, there she is. Yep, just coming in now. Okay, Nikita, I did get your materials for the student teaching. Thank you so much for sending those to me. Unfortunately, though, we didn't get to meet yet to actually go over them together. So I got those this morning around 7 a.m., and I definitely appreciate that. But for a couple of reasons, I'm going to choose to push your student teaching day back just a little bit. So one of those reasons is that I want to review those materials and go over them with you in a meeting. The other reason is that our last student teaching session left a few questions kind of unanswered. There are some things that we want to look at a little bit more closely. So today I'm going to kind of fill in the gaps from the student teaching on Wednesday and make sure everybody feels super duper comfortable. And then on Monday of next week, I'll ask you to deliver your 3.2 materials once we've had time to look at them together and talk about them a little bit. Does that sound okay with you? Wonderful. Okay, very good. Let's do it that way then. All right, then we are ready to get started. We've got everybody here, and you may notice we have an extra person with us today. That's Professor Capuano. She is my faculty mentor here in the math department, and she's just come to watch our lecture today and get a feel for how things are running in this kind of awkward online setting. Let's do the thing. As always, this is MAC2311. The section number is OH1. That is a Calc 1 honors class. And the date today is the 17th of September, 2021. Today, it's a little bit unusual. We're going to, I'll use the term button up. Let's get rid of that. We're going to button up section 3.1, proofs, and some examples. So Radha and Natasha did do a lovely job of delivering the core content of 3.1 the other day, but it was a lot of material to get through in a single lecture. It's kind of a big deal, and I think it would benefit most of us to see kind of how James Stewart's definitions compare to the definitions that you've seen in other classes, and also to look at some of the details of the proofs there, because this is an honors class. I think it's important for you guys to understand not just the mechanics, how to turn the crank, but also where these things are coming from. The proof of the power rule we went over, and we went over it pretty carefully. I feel like you guys are probably in a comfortable place with the power rule. So let me just remind you what we kind of have so far. We have the power rule, which tells us how to differentiate a power function. That says if f of x is a straight up power function, just x to the n, and originally we assumed that n was a positive integer, but we saw it extends well to rational numbers and negative numbers. If f of x is a straight up power function, x to the n, then the derivative of that function, f primed, is n x to the n minus 1. Or in Leibniz notation, we say that the derivative d dx of x to the n is the same thing, n x to the n minus 1. The other rules that we cooked up were the derivative of a constant. If f of x equals c is a constant, then the derivative f primed of x is 0. And that can be restated in the Leibniz notation, i.e. d dx of a constant c is just 0. I think these two things we should be fairly comfy with based on Wednesday's lecture. The things that we want to, that remain to be proven are the derivative of the exponential function. We looked at a bunch of pieces there, and Stewart's presentation of that material is undeniably a little complicated, and I really do want to applaud Natasha for the bravery diving into that difference quotient, pulling out the important pieces, and offering numerical evidence for the defining limit there. But rather than approach that the way the book does, I want to show you guys a rigorous proof, or mostly rigorous proof, that not only gives the derivative of the exponential as what it should be, but also connects the definition of Stewart to the definition that you've no doubt seen in your pre-calculus classes. So remaining to be shown are two theorems. And the first one we've seen some of the details of. This is just that if f of x is e to the x, where e is that number you all remember, 2.71828, blah, 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 then f primed of x, the derivative, is the same as the original function, e to the x. And Some rules relating the differential operator ddx to the algebra of the real numbers. So the derivative of a sum of two functions is the sum of the derivatives and the derivative of a constant multiple of a function is that constant times the derivative of the function. So the latter theorem here is exactly what we need, together with the power rule, to differentiate polynomials, right? If you can split derivatives up over addition and constant multiplication, and you know how to differentiate powers of x, then you automatically know how to differentiate any polynomial in the universe. And the former theorem is one of these big shot things in calculus. We really, really like the function e to the x precisely for this reason, that when you differentiate it, it doesn't change. There's a bunch of ways to interpret that, but this is one of those things that we need to get comfy with. Okay, I think the order to prove these, and I'll prove the second one first. I'll prove this guy first, and then we can differentiate some polynomials and similar things by combining that with the power rule. And then we'll prove the derivative of e to the x is e to the x. So I'll call these theorems 1 and 2. We're going to prove number 2 first. So what we want to show is that the derivative of a sum of two functions is the sum of the derivatives. So we need to begin with some expression for the derivative of the sum, and we need to end with f prime plus g prime. The derivative of this sum, you can think of some other function as being the sum of these two. So that the derivative you want is really the derivative of that new function. And we have a way of writing down the definition of this thing in terms of a limit. So here's what we're going to say. We're going to say that d dx of little f plus little g is big F primed of x, which by definition is the limit as h goes to 0 of big F of x plus h minus big F of x, all divided by h. Just like the proofs that Radha and Natasha went through the other day, anytime you need to prove something about a derivative, you got to start with the definition, right? And this is the definition of that derivative. We've just relabeled little f plus little g as big F so that it fits the notation better. So, if big F is little f plus little g, then big F of x plus h is little f of x plus h plus little g of x plus h. And then we have a minus. Maybe I'll put these in brackets. So f of x plus h is this, minus big F is just little f plus little g. And downstairs here we still have h. And remember what we're shooting for here. We're shooting for little f prime plus little g prime. So I'd like to rearrange this expression into the difference quotient for little f plus the difference quotient for little g. And all that's necessary there is distributing the negative and grouping some terms. So I have f of x plus h minus f of x. I'll just put those two next to each other. I have g of x plus h minus little g. So I'll put those next to each other. And then everything still divided by h. And then as you can with any fraction, you can take this over h plus this over h. You can split up a fraction across its numerator. There's a bunch of different ways to do it, but remember we're after little f prime plus little g prime. And I know this is the difference quotient for little f, and this is the difference quotient for little g. So we have lim h to 0, f of x plus h minus f of x all over h plus g of x plus h minus g of x all over h. And this limit here is going to everything. Right? The limit was of this whole expression, so when I split it up, each piece is still operating under the limit. And then finally, from Yiping's student teaching day, we know that the limit of a sum of two expressions is the sum of the limits. So I can rewrite this as lim h to 0, f of x plus h minus f of x over h, plus lim h to 0, g of x plus h minus g of x all over h. And you stare at this for about 10 seconds before realizing this is f prime. This is g prime. Now when we take this last step, we are making some assumptions. I'm assuming that the function f is differentiable at the input x, and I'm assuming that g is differentiable at this input x. But that's a reasonable hypothesis because the theorem is all about differentiating f and g. So it's only meaningful if they are both differentiable. And that's it. The derivative of f plus g really is f prime plus g prime. So we can declare victory. Questions on the argument here? Victory indeed.
My only
Yeah, sorry.
my only question is, when you're working with abstracts, because none of these are like actual numbers, how can you know that when you're putting in the f of x plus h plus g of x plus h, like all the way at step 2, that is actually an equivalent to big F x plus h?
Oh, well, for example, I chose the definition of big F. Right? If you wanted to, you could skip around the whole big F thing. The catch is, what is this? Right? If we're going to prove a theorem that starts with the derivative of f plus g, I need to know what the derivative of f plus g is. I need to have some way of beginning to write down this thing and then hope that it comes out to this. In order to write this thing down, I'm kind of doing a little cheeky thing where I call f plus g big F, because the only definition of a derivative we really have is the derivative of a single function, right? I don't actually have a definition for a derivative of a sum of two functions. So the choice to label that sum as big F was my choice. I made that freely.
Okay, cool. So it works because you literally said that they are equal to each other, so they can now be replaced for each other.
Right. Yep. And it's just cool. Like putting these two things in a box, right? I wrap them up and I put the label big F on that box so I can treat it as a single thing. But if you wanted to begin with this, I think 99.9% of people would understand exactly what you're saying.
Oh no, frankly, I found the big F analogy to be a lot easier to follow. I was just wondering where it's like that was the one step that tripped me.
Good. Okay, yeah, the word let is a magic word in mathematics. We have a great deal of power when we say let something be something. So that's what.
Cool.
Yeah. All right. Other questions on the argument here? So a quick example. If I wanted to find d dx of x squared plus the square root of x, we could do this now. All right? This is my little f. This is my little g. So little f of x is x squared, which means by the power rule, little f primed is 2x to the 1, which is just 2x. Little g is the square root of x, that's x to the 1/2. And I think Rada calculated this derivative for us the other day. That means little g primed would be 1/2 times x to the negative 1/2. So this derivative is just the derivative of the first plus the derivative of the second. Nothing bad. Nothing bad. In other words, the derivative does what you want it to do. Right? Anytime you have some sort of operator, it's really nice if you can split things up over addition. Just say, okay, I'm going to deal with this piece, then I'm going to deal with this piece, and then I'll put those two things together. This property that you can split up over sums together with the other property into, which we'll prove here, together those two things are called linearity. It means the derivative is a linear operator. So the other thing we need to prove here, we also want to show that the derivative of a constant times your function is equal to the constant times the derivative of your function, which would be c times f primed of x.
Doesn't that just follow with the property that we learned earlier?
That's an interesting question. For some constants, yes. Right? For integer constants, yes. Because if f and g, little f and little g, are the same, then you'd have like 2 copies of f there. But if you have a negative constant or a constant that is, not an integer, then we really do have to think of this as a separate thing.
Cool. Thanks.
So the proof here, again, I'll just call c times little f big F, because that's the thing whose derivative I'm trying to find. So say let big F be c times little f. So d dx of c times little f is just d dx of big F, which is f primed. And we have a way of writing this thing down. We know that big F primed of x is, by definition, the limit as h goes to 0, big F of x plus h minus big F of x, all divided by h. And it's going to be the same sort of symbol juggling algebra argument that we made in the previous guy. So that is the limit as h goes to 0. Big F of x plus h, well, big F of x is c times little f of x. So that's c times little f of x plus h. And big F of x is just c times little f of x. And all of that's being divided by h. And again, you stare at this for about 10 seconds before you realize, oh, factor of c here, factor of c here, I can bring it out. So inside the limit, I can factor the c in my difference quotient, and then I'll be left with f of x plus h minus f of x all over h. And again, we lean on Yiping's lesson. If you have a limit of a constant times some other expression, as long as that constant doesn't depend on the variable you're using in your limit, you can pop that constant out. So this is c times the limit as h goes to 0, f of x plus h minus f of x all over h. And this thing right here, as long as f is differentiable at the number x, is going to be f primed of x. And again, we declare victory with our little tombstone. So that's it. That's what we wanted to show. If you want an example of this thing on its own, we can ask to say find the derivative ddx of 2 times x to the 13. So here c is this 2, and my little f is x to the 13, or whatever power function you like here. This would be 2 times the derivative of x to the 13, which is 13x to the 12, or 26x to the 12. So these two things together are called linearity. The derivative is a linear operator, and we love all of our operators to be linear. The book doesn't do it, but you can express each of these things purely in the Leibniz notation also. So like ddx of c times little f is the same as c times ddx of little f. Now we have the rules needed to differentiate polynomials. Not just polynomials, but any linear combination of power functions. So, for example, yeah, a little bit. So, for example, if I want to find, let's change the notation a little bit. I want to find f primed of x, where f of x is, let's do 2x squared minus x plus 3 all over the square root of x. Believe it or not, we can do this now. The magic is to just very carefully use those rules. I'll tell you what we're not going to do. We're not going to jump up, differentiate this, jump down, differentiate this, and then cross our fingers and hope that that works, because that doesn't lean on any of the theorems we've proved. What we have proved is that if you have some functions added up, you can take the derivative of them separately, and you can pop constants out. So first I need to write this in that sort of form. And the trick here is to use some algebra, right? So wherever possible, do the algebra before doing calculus. The calculus operations can generate some pretty nasty stuff. And you want to, wherever possible, simplify your function before taking a derivative or doing some other calculus operation. So let's do it. My function f can be split up as 2x squared over the square root of x minus x over the square root of x plus 3 over the square root of x. No calculus yet. Each one of these terms can be rewritten as a simple power function using just rules for exponents. So I'll rewrite the square roots as x to the 1/2 and then we can use our properties of exponents to clean up each of these. So there's going to be a 2 here, that's this 2, And then x squared divided by x to the 1/2 is x to the 2 minus 1/2, or 1.5, which is 3/2. This minus is this minus. X to the 1 divided by x to the 1/2 is x to the 1 minus 1/2, which is x to the positive 1/2. And then finally 3 over x to the 1/2 is 3 times x to the negative 1/2. Still no calculus, just algebra. But now if I want to take the derivative of f, that means taking the derivative of this expression, and this is a sum of simple power functions, each one having some constants, a 2, a negative 1, and a 3, that we can pop out, and then just apply the power rule to this piece, just apply the power rule to this piece, and just apply the power rule to this piece. So if we want to be really careful with our notation, and in the future you likely will not be this careful with the notation, but since we're just doing this for the first time, I'll say f primed of x is d dx of this stuff. And then I can split up over these sums and differences. If we're really being careful here, I'd write this as plus d dx of negative x to the 1/2, and then plus d dx of 3x to the negative 1/2. So that's applying my sum rule twice. And then the constant multiple rule tells me this 2 can pop out, this negative 1 can pop out, and this 3 can pop out. So this is 2 times d dx of x to the 3/2 minus 1 times d dx of x to the 1/2, and then plus 3 times d dx of x to the negative 1/2. And now each of these things is something we know how to calculate using the power rule. This 2 comes along for the ride. The derivative of x to the 3/2 by the power rule is 3/2 times x to the 3/2 minus 1. 3/2 minus 1 is 3/2 minus 2/2 is 1/2. This minus 1 comes along for the ride, and the derivative of x to the 1/2 is 1/2 x to the 1/2 minus 1. That's 1/2 minus 2/2 is negative 1/2. And then from here, the 3 comes along for the ride. The derivative of x to the 1/2 by the power, negative 1/2, sorry, is negative 1/2 times x to the negative 1/2 minus 1, which is negative 3/2. And then we can clean each of these up if we desire. The 2's in the first expression cancel. So this is 3 times x to the 1/2 minus 1/2 x to the negative 1/2, and then minus 3/2 x to the negative 3/2. And once you get comfy with this rule, you won't feel the need to write out every single step like this, right? You see that, oh, the constant just comes along for the ride, and then I differentiate this piece. The constant just comes along for the ride, and then I differentiate this piece. And here the constant comes along for the ride, and the derivative of x to the negative 1/2 is this piece. So yeah, we can differentiate any polynomial, but more than that, we can differentiate any function that can be written as a sum of power functions with constant multiples. And that includes stuff like this. Later, we will have a separate rule for differentiating expressions which are fractions, right, called the quotient rule. And the quotient rule is a bit of a nasty bugger. It's one of those things that just has a lot of pieces, and it's not especially pleasant to work with. So having in the back of your mind the possibility of evaluating a derivative this way, where you split a quotient up as a sum of simpler functions and then differentiate each of those, is a good thing. You do have some problems like this in your homework to practice, and I would encourage you to practice those before we deliver the quotient rule lecture on Monday. Any questions on this?
It means if I use the quotient rule, the answer is the same, but quotient rule will, because this is polynomial on the top, so it will more difficult. So in the basic form, I use the sum rule will be better. Sum rule and different rule will be better.
Yeah, I feel like using some algebra here and the sum rule is much cleaner than using the quotient rule. The quotient rule, which we don't know yet, but if you know from previous experience, would output a pretty nasty expression, right? You'd have like a difference of two terms upstairs, each of which is a product, and then this thing squared downstairs. It's a little bit unpleasant. So wherever possible, avoid the quotient rule. I think that's a good way to think of it.
Okay.
All right. Any other questions or comments on this guy? Sarah has a good question in the chat. Should we know the proofs of all the rules we've been learning? We're in a weird kind of nebulous space in this class. So if this was just a slightly later in your math career class, I would say, yes, the proofs are everything. And if this was a non-honors class, I would say, no, you don't need to worry about the proofs. You should be prepared to make arguments that are similar in style to the arguments that we make in the proofs that I go over in class. So on your exams, there may be some questions that ask you to show or demonstrate, some fact. And on those questions, you may want to use an argument, not terribly different from what we used here, where you write down a difference quotient and split it up. But are you required to memorize the proofs? No. And I don't think memorizing the proofs is a helpful thing. Is it wise to go back through the proofs on your own to try and prove the theorems on your own? Yes, absolutely. I think that will help your understanding.
So actually, here we make the proof. It just help us memorize those forms will be better. But it doesn't mean we need to make a proof for have an exam in this proof.
Yeah,
this kind of basic proof.
Yep. I think one of the nice things about going through a proof of a theorem is that it helps you remember the theorem, right? If you know why something is true, then it's a lot easier to just remember that it is true. So on the one hand, yes, they will definitely help you memorize the theorem, which is useful. The other thing is kind of a philosophical thing. I don't know about you guys, but I don't like to do a lot of work unless I know that the work I'm doing is logically sound. I get nervous if I start building a house without measurement. I'm not the sort of person to break out the hacksaw without at least drawing where I'm going to cut. So proofs of these theorems are what guarantee us that what we're doing is kosher, that it's not breaking some mathematical rules, that it's logically consistent and sound. So the proofs can set you at ease in that way. But if you're just thinking about the utility, it's also a helpful way to remember the theorems themselves. All right, that's I think enough discussion here. Let's go ahead and look at the other piece. So Stewart does something. It's not unforgivable, but it's really not nice. And we talked about this briefly the other day, but we didn't really have time. So the other theorem we want to prove says, if f of x is e to the x, then f primed of x is also e to the x, where e is this fancy number, 2.71828, blah, 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 blah. Stewart's proof, which is the proof that Natasha was beginning on Wednesday, relies on a weird definition of the number e, and also kind of tries to foreshadow a lot of things without actually getting into it. So what I'd like to do is just run through the proof directly. And then I'll connect Stewart's arguments to the definitions of the number e that you've seen previously, just so things are cohesive. So, f primed, the derivative of this function, derivative of any function, is f of x plus h minus f of x all over h. We should be getting pretty tired of seeing that now. Which is the limit as h goes to 0 of e to the x plus h minus e to the x all divided by h. And this is the limit as h goes to 0. Remember, we have some algebra rules. If I have some number a raised to a sum of two other numbers, b plus c, that is the same as a to the b times a to the c. This is just a rule for exponents that I'm sure you've all used in your pre-calculus classes, which means that e to the x plus h is the same as e to the x times e to the h. This minus is this minus, and e to the x is e to the x. And like in our proof of the constant multiple rule, I have a factor that is common to the two terms upstairs, namely e to the x. So I get lim h to 0. I'm going to factor in e to the x out, and what will remain upstairs from this term is e to the h. This minus is this minus, and when you factor e to the x out from this piece, you just get a 1. All of this is over h. Now remember what we said about the constant multiple rule for limits. If this was like c, then I could take it out past the limit. But what does it mean to say that thing is a constant? It means it doesn't involve any of this variable. So e to the x here, this piece, is a constant with respect to the limit. It's not constant with respect to the variable x. You change x, this thing changes. But as you change h, this thing does not change. And this limit doesn't have anything to do with the variable x. We're sending h to 0. So with respect to this limit, this piece is a constant. So he can come all the way outside. And then we have lim h to 0, e to the h minus 1 over h. And this is where I want to take a quick second to pause. Stewart defines the number e to be the unique choice of base here that guarantees this limit will come out to 1. That's not the definition of the number e that we see in pre-calculus classes. It's not a definition of the number e that in any way is insightful. Natasha yesterday showed us that if you plug in a number smaller than e, so let's write some of this down. Stewart says that b equals e is the unique number yielding lim h to 0, b to the h minus 1 over h equals 1. And this is what we saw some numerical evidence for the other day. So I think Natasha plugged in 2 for b here and saw that this limit came out to something like 0.69. She plugged in 3 for b here and saw that this limit came out to something like 1.1. And so the argument is that somewhere between 2 and 3 there should be a number we could plug in for b here, which will give us 1. That for some reason this is a monotone function of b. All of that is, in my book, a little suspect. Right? It doesn't feel good. So what I'd like to do is show you that this limit is 1. And to get there using the definition you're familiar with. So on the one hand, we could say, yeah, this is 1. This is 1 by the definition in the textbook, therefore this limit is e to the x. Let's go ahead and write down the result we would get with that. So this limit being 1 means that the derivative, f primed, which is the derivative of e to the x, would be e to the x times 1, which is e to the x. But all of that rests on this claim that the limit as h goes to 0, e to the h minus 1 all over h is equal to 1, is a suspicious claim. I hope you would agree. So instead of just assuming
tidy.
Oh, I'm sorry, Sarah, go ahead.
It's conveniently tidy.
It is, yeah,
But
and
not
this is
convincingly.
something math authors do this all the time. They're like, oh, well, I can just like kind of shove this in here and say that's the definition we're going to work with, but it's skeezy as all hell. So instead of that, let's prove the claim separately, and then we'll look at some examples. I think I outlined this for you guys the other day, so I don't want to burn too much time on it. So the last thing before we can actually start working with this is we need to prove the claim. The standard definition of E is as the limit n to infinity 1 plus 1 over n all to the n. So what I'd like to do is show that this and this are equivalent. We can substitute, let's see, 1 over n for h. So how is it conveniently tidy? That's good. So the derivative of e to the x turns out to be e to the x times this limit. And a priori, the textbook author knows that the derivative of e to the x is e to the x. He's not like discovering this as he goes through the proof. It's a fact of calculus that's revered and loved by all mathematicians. So he knows that this thing needs to come out to just e to the x. And when you start writing down the difference quotient, pretty quickly you get to this place where you've got e to the x, the thing you want, times this pretty intractable limit. This limit that you definitely aren't going to calculate by plugging in 0 for h or anything like that. So you know that this whole thing here should be e to the x. You've got e to the x right here. Shit, wouldn't it be nice if that was 1? So Stuart just goes, yep, that's 1. That's the definition of e. See ya. So that's the sense in which it is suspicious and conveniently tidy, right? It's like, this is really fucking hard. Wouldn't it be nice if that was 1? Yeah, let's say that's the definition of e. All right, now that's 1, and we can just move on. You can memorize the form. That's an option too. Some people, no doubt, come into calculus knowing that this should be 1. I wouldn't claim otherwise, but I think a very small fraction of people. I think probably a larger fraction of people, rather than knowing that that limit is 1, know that this thing is e. Because this is the definition we use in pre-calculus classes. When you study compound interest, you end up studying this as a function of n. And you discover that as n gets larger and larger and larger and larger, you get that continuous compounding formula, which involves the number e. So here's what I'd like to do. I'd like to let, there's that magic word again, I'd like to let h be 1 over n. And observe, as a consequence of 2.6, that h goes to 0 as n goes to infinity, right? Remember that theorem from 2.6? 1 over x to any positive power will go to 0 as x gets large. This is the same thing. As n gets large, 1 over n is getting smaller and smaller and smaller. So if I define h to be 1 over n, as n goes to positive infinity, h is going to go to 0 from the right, in a positive way. And then I'm going to sort of restructure this in terms of the variable h. First, if h is 1 over n, then this piece right here is h. And this power up here, n, is 1 over h. So what we have is that e is equal to the limit as n goes to infinity, 1 plus 1 over n, all raised to the nth power, which is the same thing as saying limit h goes to 0, 1 plus h, all raised to the 1 over h. All right, so let me write it like this. Now the step that I'm about to show you here is not 100% rigorous, right? It's not delta epsilon rigorous, but it should be pretty convincing. This e over here could just as easily be a lim h to 0 of e, right? The limit of a constant is that constant. And I can raise both sides to the power of h to kill this exponent. So I claim that this is at least close enough to reasonable that you should be convinced by it.
I cannot understand why the e is equal to limit h approach infinite, parenthesis 1 plus 1 over h, parenthesis to h, and suddenly become the limit h approach 0 and 1 plus h to 1 over h.
So this is an n.
Okay.
They look quite similar, I know. But the variable here is n going to infinity, little n, and here this is an n, and here this is an n. And what I'm doing is I'm making a substitution. I'm choosing to relabel the variable n as the reciprocal of h. So 1 over n is equal to h, and h is equal to 1 over n. So I'm going to re-express this limit, which is a limit in terms of the variable n, that is usually used as the definition of the number e, in terms of this new variable h. Maybe, what can I do to make the h stand out? You guys are going to hate this when you take physics. Let's call it h bar. Here, we can put a little tag on the h so we can tell the h is from the n's. All right. The dubious step is definitely this one. This is the place where I'm kind of hiding some things. Raising both sides to the power of h here is at best a little sketchy, but it's a reasonable algebra operation if you eschew the limits, right? Absent the limits, this is certainly true. And with the limits, it's true as well. It just looks a little scary. Okay, so if h, or h bar, is 1 over n, cross multiply. That's the same as saying n times h is equal to 1, which is the same as saying n is equivalent to 1 over h. So saying n is the reciprocal of h is the same as saying h is the reciprocal of n. So I'm literally just plugging in. This n is equal to 1 over h, and this 1 over n is equal to h. Bueno? Very good. Okay. We're almost there. We're almost there. If you look at this expression, you might start smelling the Stewart limit within it. Let me see. Oh, did I miss something? H minus 1 over h. Look, I am missing something. All right. So this would be... Oh, no, this is good. Yeah. So this is lim h going to 0. Now I'll subtract 1 from both sides. Again, just pretend like the limits aren't there as we do this, if it feels wonky to you. And you'll see that the algebra is kosher. And then finally divide both sides by h. H, a little mark.
I have questions for the second limit h approach 0 and e to h is equal to limit h approach 0, parenthesis 1 plus h, parenthesis. Is it because h approached 0? So the degree on the top 1 over h is going to the infinite.
I want to make sure I'm understanding the question right. So is
Going
the question, are we asking how did we go from here to here?
Yes.
I'm raising both sides to the power of h. So in passing from here to here, like you can square both sides of an expression, you can cube both sides of an expression. I'm raising this to the h and raising this to the h. On the right-hand side, when I raise this to the h, the 1 over h goes away. This is like the hth root. So like squaring a square root or cubing a cube root gets rid of that root. When I raise this side to the h power, I just get 1 plus h. And when I raise e to the h power, I get e to the h. Does that feel a little more comfy? I can insert the similar things for each other step here. Here we're subbing n equals 1 over h and h equals 1 over n. And then here we subtracted 1 from both sides. And for my next trick, I'm going to divide both sides by h. This will give me lim h to 0 e to the h minus 1 over h equals lim h to 0 h over h, which is 1. Oh, and h bar thingy. Okay. And then finally, the limit on the right is a limit of a constant. Which is Stewart's definition. So that's the job done. So now we can trust the tidy part. Yes, exactly. That's precisely it. The tidy part is no longer suspicious, it's now just tidy. And that's what we like in our proofs. Yeah, good stuff. Okay, all of this is a long way of saying the derivative of e to the x is e to the x. Other exponential functions, b to the x for other values of b, which we did hear about a little bit in the student teaching from Wednesday, we'll have to wait a little while for us to differentiate those. The slick way to get those derivatives is to use something called the chain rule. You notice we never had to make any arguments about f prime of 0 here. We didn't have to use any numerical evidence to convince ourselves that something is kosher. This is where my preferences differ from the preferences of the textbook author. But I hope that you guys feel a little bit more comfortable with the proof that Natasha presented yesterday. So I think these sort of background things are not obvious, right? Not at all obvious. So let me see how we're doing for time and look at a handful of examples before I have to let you guys go. First, just something straightforward. Let's do let's just calculate the derivative. And this time, instead of being exceptionally patient and writing out every little step, Let's try to do it a little more efficiently. I'm taking the derivative d dt of this expression, which is a sum and difference of little pieces. Each one I know how to differentiate. First piece is a straight up power rule. This piece is a constant times a power, but maybe we want to rewrite that as a 1/2 power first. This is a constant times e to the t, we know his derivative. And this piece is just a constant. So d dt of this big thing I'll tell you how I like to do this. If I have to split something like this up and I want to write out the steps, but without getting my hand to cramp up or making this godforsaken callus on my finger worse, I use the prime notation. So I'd say this is t cubed primed minus 3 times t to the 1/2 primed plus 7 times e to the t primed minus 5 primed. And we'll use this sort of schematic in the future where we denote the derivative of an individual piece with the prime. So this is just short for d dt of t cubed, and minus 3 times d dt of t to the 1/2, and so on. Each one of those we can crunch out using the power rule. So this is 3 times t to the 3 minus 1 is 2. Then here I have minus 3 times 1/2 times t to the 1/2 minus 1 is negative 1/2. Then plus 7 times the derivative of e to the t is e to the t. What's the derivative of 5?
Isn't it
0.
Very
0.
good, very, very good. Minus 0. While we're here, this is something I used to put on tests all the time and catch about half folks out. Is it true or false that the derivative dx of e to the pi is e to the pi?
False.
Very good.
0.
Yeah, excellent. This is false. So Yuping's correct. Why is this false?
Because e and the pi, they are constant.
Very good. Like e to the pi, it's like 2.7 raised to the 3.1. It's just some numbers, right? 2.7 like raised to something around 3.1 is a constant. There are some problems in your homework that are meant to suss out this sort of subtlety also. So it's not the case that every time you see an e and you're asked to differentiate, you're just going to copy down the same thing. You do need to think about it a little bit. There are also some really bad groany memes out there on mathematics Facebook sites where you differentiate something like d dy of e to the x. I understand what you're saying, David, but the notation could be a little bit confusing. So we wouldn't say that f primed of e to the x is e to the x. This statement here, and don't write this down, this is kind of mixing notations. So what would be true is that e to the x all primed is e to the x, which is the same as saying d dx of e to the x is e to the x. Or if you want to invoke the function notation, you could say if f of x is e to the x, then f primed of x is also e to the x. Any one of these would be a valid way of saying that. Yeah, and the idea there is that x is a variable. Well, conveniently, the notations aren't saying different things. So this is what David typed in chat, and I think what he was saying is that the derivative of e to the x is e to the x. But it's this is a confusing mixture of notations that that does not quite make sense. So I would not write this down. All right, this is not correct use of notation. And one of the things we really do have to get comfortable with in this class is the notation that communicates the calculus effectively with other readers. So remember, the prime and the ddx, those are commands. They're verbs. They tell you to do something. So when I write e to the x all primed, I'm saying I'm going to take the derivative, prime, the function e to the x. And the Leibniz notation says exactly the same thing here. I'm going to take the derivative, d dx, of the function e to the x. And both of those just come out to e to the x, right? So derivative e to the x is e to the x. Yeah, we would not want to put the contents of the function as the argument, right? The argument is the variable, right? So the variable or argument of the function e to the x is just x. F of e to the x would be like you take your original function f, whatever that is, and everywhere there was an x or whatever the original variable was, you shove in an e to the x. That's communicating something very different. All right, let's take a look at one more challenging problem, something that requires us to not just calculate a derivative, but do something with it. I'll grab one from your textbook before we have to get going here. We talked about calculating tangents and calculating normals a little bit. Oh, hey puppy. Yeah, I like this one. Okay, find the points where we have horizontal tangents. So we're going to find the points where the curve y equals x to the 4 minus 6x squared plus 4 has horizontal tangent lines. All right. So we don't just have to compute a derivative here, we need to interpret and understand the derivative. I would begin this by saying that the slope of the tangent line at x equals a is f primed of a. So the curve y equals x to the 4 minus 6x squared plus 4 is the curve y equals f of x, where f is that function. So if I'm looking for horizontal tangents,
Derivative is equal to 0.
very good. Means I'm looking for a place where f primed of a or f primed of x is equal to 0, i.e. solutions to the equation f primed of x equals 0. I should say horizontal tangent at x equals a, if I'm being careful over here. All right, so a line in general is horizontal if its slope is 0. That's the same for a tangent line. A tangent line is horizontal if its slope is 0. So what we're looking for are places on this curve where the tangent line has slope 0. And since the tangent line's slope is given by the derivative, we're looking for places where the derivative is equal to 0. And when I say a place or a location, I'm always referring to the input. Where does this happen on the graph is always for what input. But the problem specifically said find the points. So in addition to finding those x values that solve the equation f prime of x equals 0, we need to determine the point on this graph that has that x value once we've found them. So precisely like being said, horizontal tangents, set the derivative to 0. That's what we're looking for.
I think it's 4x to 3 minus 12x is equal to 0. Solve x and then put the x in the origin equation, get the y.
This is good. Yeah, let me back up just a little bit. So if we're going to call this thing f of x, then the derivative f primed of x we can calculate using the rules from the section. And yeah, this guy is going to differentiate to 4x cubed, minus 6x squared is going to differentiate to 12x, the plus 4 goes away. My recommendation here is to then factor this. So I've got a common factor of 4 and a common factor of x, both of which can come out. And then what's left here is an x squared minus 3. The x squared minus 3 I can factor further as a difference of squares. That's x minus the square root of 3 times x plus the square root of 3. So what I'm doing here is I'm forcing this into the form a squared minus b squared, because I know that always factors as a minus b times a plus b. So 3 may not be a perfect square, but it is the square of root 3. And then we can read off right away the solutions to f prime x equals 0. Those are the roots of this expression. If this factor is 0, which would mean x is equal to 0. If this factor is 0, which would mean x is equal to the square root of 3. And if this factor is 0, which would mean x is equal to the negative square root of 3. So those are the values of x that give me a derivative that is equal to 0. If I want to find the points on this curve, then I need to take these x values and plug them into that original expression. Let's say hence the points where y equals x to the 4 minus 6x squared plus 4 has horizontal tangents are, well, when x is equal to 0, y is equal to 0 to the 4 minus 6 times 0 squared plus 4, which is 4. So we've got the point 0, comma 4. That's one of them. When x is equal to the square root of 3, y is equal to root 3 to the 4 minus 6 times root 3 squared plus 4. What is the square root of 3 raised to the 4th power?
9.
Very good, yeah, 9. And then we've got minus 6 times the square root of 3 squared, 18, and then plus 4. So 9 minus 18 is negative 9, plus 4 is negative 5. So the point associated with x equals root 3 is root 3 comma negative 5. And then finally, when x is equal to the negative of the square root of 3, we could actually save some time here by observing that this is an even function, right? It's a polynomial and all the powers of x are even, or you can just do the evaluation. The fact that that's an even function would tell me what?
The negative is equal to positive.
Yeah, the output at negative root 3 is the same as the output at positive root 3. In other words, I know I'm going to get negative 5 again. But we can do the calculation, it won't hurt us. So negative root 3 to the 4, well, it's an even power, so the negative is going to get gobbled up. This is going to be 9 again. And then the negative square root of 3 squared, again, is going to be positive 3, so this is 6 times 3 is 18. And then adding 4 is adding 4. So you see we get exactly the same thing. And the point there is then negative square root of 3 comma negative 5. Alrighty, and that would be the game. That's the whole thing. So the power rule is your friend. exponential functions, even more so, are your friend. I've heard professors at MIT say, there's only one kind of function that anybody is willing to differentiate or integrate, and those are exponential functions. Today we see why, right? Because the derivative of the natural exponential, at least, is itself. Next time, Nikita is going to teach us how to use the product and quotient rules. That'll be a lot of fun. Remember, when you're looking at differentiating a quotient, to first try to do some algebra. There are some problems that are in your current homework that you may be tempted to apply the quotient rule to. But remember, we haven't discussed those in class yet. Technically, you have to pretend like you don't know the quotient rule yet, and genuinely, the faster way to solve those is by doing the algebra first. Is there anything that you guys would like to ask me before I wrap up for the day?
Will you have office hours today?
That's a great question. So I do have a department meeting this afternoon, so I'm going to have to move the office hour to a little bit later in the day, but I will have an office hour, and I'm going to post an announcement to Canvas to let you know exactly when that'll be, probably around 4 p.m. instead of 1 to 2.
Thank you.
I had a quick question. Oh, go for it.
Sure, yeah.
Okay. I know we have like a test next Friday, right?
We are getting close to the first test. So we mentioned this at the very start of class. We need to get through the chain rule before exam 1. And between now and that, we have 3.2 on the product and quotient rules. We have 3.3 on derivatives of trig functions, and then 3.4. So my expectation is that by next Friday, we will have finished 3.4. Now, that doesn't mean we're going to have the test on that day. That means I will supply you with the study materials, the extra study materials, the study guide on that day, and then the test will be the following week. We have not set the exact date for the test yet, so on this day, the 24th, I expect us to finish all the material for the first test, which means exam 1 could take place any of the class days the following week. I generally like to give you guys at least a few days with the study guide. You'll have the whole weekend there, but Monday feels a little tight. Probably it will be either Wednesday or Friday of that week, and I will let you guys vote on which day to have that test. So I think on the 24th, on the day we finish the chain rule, I will let you guys pick between these 2 days for the test. So look at your work schedules, look at what else you have going on in your life, start thinking about when you think would be better for you. But it's not next Friday. We still have a little bit of time.
Okay. Yeah, and then so I know like if you want to take the test in person, like do we just email? Like I know you said we have to like kind of do something to set that up.
Yep, that's exactly it. So send me, I prefer a Canvas message.
Okay.
Send me a Canvas message saying, hey, I want to take the test in the testing center. Can you schedule that for me? And I'll do it. If you want to take the test online, remember you're going to have to use Zoom on your phone in addition to HonorLock on your computer. And I'll walk you guys through the details of that when we get a little closer. If you want to avoid all of my hard-ass proctoring rules online, you can always take the test in the testing center. And that just requires you letting me know ahead of time so I can schedule it for you.
Will you post the study guide earlier today for some question?
I will post it as soon as I can. So like I said, I do have a meeting I have to get to, and then I actually have a doctor's appointment thingy that I gotta run to. But I promise you, before I go to bed tonight, I will post some version of the study guide. And that will be updated later as I see how you guys are getting through the homework. But there will be something up by the end of the day today, yes.
Thank you.
Sure. Week after next, David. Week after next. Anything else, gang? Alright, remember as always, if you need help, send me an email, a Canvas message, or post on the Discord. Discord is a little dry for this class so far, but you guys have each other to lean on there as well. I strongly encourage that. Or you can come by the office hour. Office hour today is going to be at an abnormal time, but I will post an announcement letting you know exactly when. If there's anything else you need, please don't hesitate to reach out. I'm here for you. You're here for each other. Just keep working on that homework and hang in there, all right?
Thank you.
Of course. Take care, guys.
Thank you.
You okay? I am done, yeah, but Bettina came to observe today, so I wanted to hang out for a second and see if she wanted to talk. William, David, you guys doing all right?
Whatever's convenient for you, we can talk another time and you can deal with them right now.
Okay, yeah, I'll send you an email. We can set up a different meeting if that's good for you.
It's fine.
All right. Hey, David, did you need to talk about something? Okay, if I click